So I'm recording now, just so you guys know. So anything you say from here on, people will hear. So I'm gonna go through. We're gonna start at module 9, which is where we're past the second assignment after the ANCOVA, after the t-test. If you are confused about anything that's in modules 1 to 8, so that would be your levels of measure is really important. I still was getting papers to edit this week that had levels of measure wrong. Like it's key. Like you have to be able to understand that. So if we need to go over it again, let me know and I will. Otherwise, go back and watch the first video. Measures of central tendency, measures of variability. You have your contingency tables, scatter plots, the Pearson R, then your standard error, steps of hypothesis testing, all the stuff about errors, your t-test, and your ANCOVA. So I'm not going to go over all that, but you have it in the other videos. So hopefully you can go back and watch those. And actually, before I start, if you really feel like you're in a really, really bad place coming into this exam, give me a call. It's not right now because I'm recording, but in the next day or two, we can talk it over a little bit. But I think you should be okay just from this. If not, if you're terrified, give me a call. Okay, so let me just close this off here. You can see. Can't really see your chats, but that's okay for now. Okay, so up until now, we've been talking about parametric tests, right? Those are the ones, those are your t-test, your ANCOVA, Pearson R, what we talked about earlier. So the chi-square is actually a non-parametric test. And there are a bunch of these. We don't need to know. Actually, you don't even use them in the course, but you'll need to know a couple of them. They're listed here. So really the big thing about this is that you're looking at how often something is showing up, right, in categorical data. So you've got two nominal variables or a nominal and an ordinal. Sorry, 1 second. Are you leaving because I'm too annoying? Okay. My husband was trying to do his work in here too. Apparently that was not going to be possible. Yeah, so you might have two nominals or a nominal category or nominal and ordinal, whatever. What we're basically, I found the way they explain this to actually be quite confusing. But it's basically telling you if there's a statistical significance in terms of the relationship between two categorical. So if you look at RNs, right? RNs and RPNs, diploma, RNs, diploma or bachelor. Or if you look at the second one here too, this is actually easier. You have with diabetes, with cancer, with heart disease, right? Those are all yes or no nominal variables, but you can still make inferences from them. You just have to figure out the proportions, and we'll go through it in much more detail so it'll make more sense as we go. So what we did earlier was our frequency distribution and contingency tables, which is nice because you can describe the information, but without the chi-square, you can't make any inferences. So it's the same as when we talked earlier about the Pearson R. You have your Pearson R that talks about, is there a relationship? If there is, how strong is it? What direction is it in? But you can't make an inference from that because you need significance testing. This is the same thing. You've got categorical variables. You've done a frequency count. You've done a contingency table, but you can't make any inference until you do this chi-square, okay? Frequencies in each cell happen by chance. Okay, this is better explained way down here, so we'll just skip down there. So she only, I think, talks about the two, just a few different kinds of, oh, no, sorry. a few different kinds of chi-square tests. So this is one of the purposes of a chi-square. Okay, so don't worry about all of this. So a lot of this is just like my notes to make it make sense to me. So I kind of went through and highlighted the stuff that makes sense, I think, for more than just me. So the goodness of fit. That's my husband blowing his nose. You're being recorded, babe. He doesn't care. Okay, so the proportion of something in your sample, is it equal to the proportion of that same thing in the population? So you remember we talked earlier about your standard error? It's a very similar concept. Is the proportion of, we have 100 people, 50 of them have diabetes. Is that representative of the proportion at large, or population at large? Obviously not, because 50% of the population doesn't have diabetes, right? Again, if you're doing the RNs with degrees versus diplomas, you know, you want what you have in your little chart, which is going to look something like this one here. You want those numbers to kind of represent what's out in the real world. And that's why you would do this goodness of fit. So if you have a question on the exam, it's asking you, how do you know, you have two categorical variables. How do you know if it's representative of the overall population? You're going to do a goodness of fit chi-square test. Okay. And that's really all you need to know about this. In this case, your null hypothesis is that the sample is the same as the target population. And then your alternate would be that it's more or less, right? So your null is basically, yes, it's representative. Your alternate would be that it's not, right? Yeah, and again, this is just explaining the same thing in different ways, so you guys can read through it. So what if you don't know the proportion of like whatever you're measuring, it's not something that's ever been measured before, so you don't know what the proportion is in the population, then your null for goodness of fit would be that there are equal proportions inside of your data. So if you look down here, okay, actually don't look down there, it'll confuse you. Say you're checking the frequency of diabetes, heart disease, and cancer. Pretend we don't know what that is in the population. So your null in that case would be that there are equal numbers for each group. So you have 10 people with diabetes, 10 people with heart disease, 10 people with cancer in your sample. If, again, that's only how you do goodness of fit if you're not aware of the proportions out in the real world, which I'm not sure that will ever come up, but just in case. And then your alternate would be that, you know, it's uneven. More people have diabetes than have cancer, or, you know, you have 20 people with diabetes and 2 people with cancer. And in that case, you want to know if it's statistically significant. The reason for that is if you have taken a group of 100 people and you're measuring and you're counting the frequency of diabetes and heart disease and cancer, if you've done it by chance, you should have relatively equal number in each, right? Because the law of probability that we talked about in earlier videos states that when you do random sampling, you're at a higher chance of you have more of a chance of getting a representative population, right? A representative sample. So the goodness of fit basically compares the difference between what we see in our sample with what we would expect to see if the null were true. So it calculates the difference between your sample and the proportion or out in the world, or it calculates the difference in your sample between your sample and if they were all equal, right? If they were all equal, because you don't know the proportion out in the world. Do not worry about this stuff. That's just me writing down things to try to understand them. and I don't even think I did. So this is how we do that. We test for independence. So you have two variables, okay? You want to test the relationship between those two variables, right? Now, in this case, those are categorical variables. Obviously, if you have a continuous and a categorical, you're going to do a t-test. If you have two continuous, you're going to do a Pearson R. We're talking about like down here, male and female and experiences of abuse, right? So it's yes, no, and male, female. You have two dichotomous nominal variables. So you want to know if there's a relationship between these two. You know, are females more likely to become abused than males? Okay. So your null would be that there's no relationship. They're completely independent of each other, which is why we call it an independence test, or that there is a relationship. So again, we're back to our normal null and alternate hypothesis. Don't worry about this math at all. Neither do you need to worry about this. I like my little notes here. So this is all going to be explained better, but you want to find the expected frequencies. You want to know what would be normal, right? So I know this looks confusing, but it's because it didn't make sense to me and I needed to make it make sense. So there's this little expected frequency is the frequency of the column times the frequency of the row divided by the sample size. Don't panic. Let's explain it down here, okay? So here we have this nice little distribution table, right? And we've got two different variables. We have the diseases or diagnoses, right? Which again are nominal, is just cancer, heart disease, diabetes. And then we have these levels of like ADLs, right? And this is an ordinal because we're going completely dependent, some assistance, completely independent. So ordinal and nominal, we want to know if there's a relationship. We can't do a t-test, we can't do an ANCOVA. So we make this lovely little chart here. This is our population. It looks like our population total was 30 people, okay? And then just fill it out. So the number of people who have cancer and are completely independent is 5. The number of people who have heart disease and completely independent is 1. If you want to know the number of people who have diabetes and completely dependent, that's 9, okay? So if you want to calculate the expected frequency of, let's say, a completely dependent person with cancer, so what should be here, well, sorry, let's do that first. So we're going to do that little, remember up here, I was saying there's this little expected frequency, it doesn't really make sense. We're going to do that little thing here. So you take, so this is what we're worried about right now. The people with cancer, so this row, who also are completely dependent. So this, sorry, this row, this column. Okay. So you would take the, I just want to make sure I've got this right. Yes, yes. So where's this 7 coming from? Okay, so the 7 is coming from the total of this row of completely dependent people, right? There are 7 completely dependent people in the entire study, okay? Then the 8 comes from the total of people with cancer. So you have 8 people with cancer in the study, 8 out of 30 people. So you're going to multiply that 7 times 8, and then you're going to divide by 30. And that gives you, in this case, it gives you 1.9, which is nicely given to us here in the chart. That is what the number would be if the null were true. Okay, so, and I actually, oh yeah, okay. So just hang on to that. It'll make more sense as we go along. So because the data isn't continuous, this is where you guys can have a weird curve with no two tails. Everybody was really, really anxious to have one-tailed tests on your last assignment. And remember, I was saying it's pretty rare, but in this case, because you don't have continuous data, you're not going to have, whoa, oh, guys, mute yourself if you're just chiming in. Just mute yourself so that we don't have giant echoes. Thank you. So yeah, so you're going to have this really weird curve that doesn't really look like a normal bell curve, but you still have your little critical region, your tail. So again, you can't do a two-tailed test. You're still looking for the sorry, I say it and then I look down and I wrote it and I feel like I have to read it again. So the shape of this will change depending on the number of categories, whatever. You don't need to worry about that. Obviously, there's not going to be any negative values because your numbers have no mathematical meaning, right? So in order to calculate the degrees of freedom, this was another area where I found a lot of people were struggling. So just make sure you go back to the first two videos and really, really understand how to calculate degrees of freedom for the different tests. They're all different. Your ANOVA is different than your t-test. Your t-test with a paired sample is different than your t-test with an independent sample. Your Pearson R is different. Go through all those notes and make sure you know how to do them, because I mean, I would think they would come up. If I were writing the test, I would definitely put a lot of those in. Those and the levels of measure. Sorry. So you're taking the number of rows minus 1 times the number of columns minus 1. So if we go back up to this here, we've got 3 rows, 3 columns. So 3 minus 1 is 2, 3 minus 1 is 2, 2 times 2 is 4. So your DF, right? Let's make sure. Number of rows times the minus 1 is, yes. So we'd have 4. And then you use that DF to determine the shape. You don't need to worry about that. You can't. So this is what the chi-square looks like. This isn't from Excel. I don't remember what the name of the other program is, but it's from the other program. Again, the only thing you really need to know is to be able to pick out your critical value, your degrees of freedom, and your calculated test statistic. Okay, so you do a whole chi-square. It's going to come up just like when you do a t-test. You're highlighting, you're putting the information in, and what comes out is this chi-square result. Okay, so your value is 10.58. This is the frequency or the of whatever it is that you're looking at. Your degrees of freedom is 4, and the significance is 0.039. Again, it's just like the Pearson R. The critical T, like this cutoff, they don't give you that. You have to go to the textbook. You have to look at the universal chart and figure out what it is. But let's just say your critical chi is 9.2. Oh, can you guys mute if you just logged on? Actually, I can probably mute. Oh, awesome. Thank you. So if your critical is 9.2, you came up with a 10.58 at a p-value of 0.039. So your value here is higher than your critical chi, and your p-value is 0.03, which is less than 0.05, which means it's significant. You're going to reject the null. Okay, so all of this that we just talked about it's a little bit more complicated than what I remember being in the exam. I don't remember like even having to, I don't remember if we had to like calculate these out, but make sure you kind of understand the concept of this, like this, you know, you're going to go the total of the rows times the total of and that's how you find out the expected frequency. Okay, if you have a question about expected frequency, that's how you calculate it. If there's a chi-square question, it will probably look like this. It'll probably give you the little thing and it'll tell you the critical, and then you have to decide if you're going to reject or accept the null. And that's the same pattern no matter what test you're doing. So you guys should be awesome at that now. Okay, and then this little green arrow, it's pointing at this 7 cells, 77.8 have expected count less than 5. So with a chi-square test, it's just really, really important that your sample size is large. The cutoff is generally around 5 for each each one of these, right? You don't want to have less than 5. You have less one all over the place in this chi-square. Sorry guys, my throat's been a little bit sore the last couple of days. Okay, goodness of fit. So you get a question, it's talking about goodness of fit or a test for independence. We are talking about chi-square results. Okay, you need to, if you're going to report the results, you need to state the type of test. So was it a goodness of fit test or an independence test? Now remember, the goodness of fit is testing for how representative is this of the population. And then independence is more the what's going on with this population. Is it a significant finding, right? Is there a significant relationship between between two different variables? Does that make sense? I feel like I'm going around in circles because I hate this chi-square stuff. So again, goodness of fit is about, is this variable, the amount of this frequency of this variable that I'm looking at, cancer, heart disease, whatever, is it representative of the population in general? If that's a yes, awesome, right? That's the null is accepted. If it's a no, you reject the null. The test for independence is taking two variables. Whoops, sorry. I keep swinging all over the place. Taking two variables, both categorical, and saying, is there a relationship between these two variables? And then you're doing this, the same, basically the same thing you've done up until now, okay? I feel like I've explained that over and over again because it's not the most clear. So if you don't have it, let me know and I will repeat it again at the end. But anyway, in order to report it, did I do a test of goodness of fit or a test for independence? What was the calculated test statistic? What was the degrees of freedom? And then what was the p-value? Same thing that you do with every other test, okay? And you remember when we did a t-test and ANCOVA, we had a list of criteria. In order to do them, you needed to have, this many variables are continuous, this is categorical, whatever. For the chi-square, you have this similar list of criteria. And again, we talked about, sorry, I keep scrolling, that they have to be categorical. These are kind of rules that also must be there. They in order for it to be a chi-square, for it to calculate the chi-square, right? So one outcome cannot affect other outcomes. One outcome cannot be classified in one category. It can only be classified in one category or the other. So you're either male or you're female, but not both, right? Again, I don't remember anything about this coming up, and I wouldn't worry about it. I feel like the test is heavier on what you've done so far already, and then these multivariate statistics that we'll talk about later. Okay, this is the stuff that makes more sense now. I'm gonna go through this really fast because it's in another video as well. But you've got your Pearson R correlation. So again, your Pearson R is only telling you if there's a relationship, and which direction it's in and how strong the relationship is. It doesn't tell you the significance of that relationship, right? The statistical significance. So you have to do a Pearson correlation or a Pearson R with significance testing, okay? You did this in your last paper, so I'm not going to go too crazy into it. If you guys have questions, go back and check the other video. Or if you have questions, you can ask me now. I'll just keep moving. Okay, so when we're talking multivariate statistics, so, Like, so people get really confused with this because they say, well, we were already doing multivariate because in our ANOVA we had 3 categories. And then, okay, so what we're talking about here is multiple variables. What we had in ANOVA was we had 2 variables, but the independent variable was separated into categories, and it was more than 2 categories. So we had to do an ANOVA, okay? This is talking about, we actually have 3 or 4 or 5 independent variables now. So we're looking at what are the effects of, I'm gonna make something up. What are the effects of workplace violence, bullying, and shift work? So there's 3 different variables there on retention, right? On nurses actually quitting or actually staying or quitting or whatever, right? So you've got one dependent variable. Your dependent variables, well, you want to know, what's affecting nurse retention. Well, you want to know how much of that is caused by burnout, how much of it is caused by violence, how much is caused by shift work or whatever. Those are terrible examples, but hopefully that makes sense. Your independent variable now has more than one. Okay, so we're going to do a factorial design. The reason we call it a factorial design is because they're just referring to your independent variables as factors. So what factors are affecting nursing retention? Is it this? Is it that? Is it the other thing? And we'll go through it. So it's really similar to an ANOVA, but it measures the effect of each variable, each independent variable on the dependent, and then it combines all of the variables and tells you how much, what the effect is on the dependent variable as well. So you get two kind of different groups of effects. You have your main effect, which is each independent variable's effect on retention on its own. And then you have an interaction or a combined effect, which is all of those things together, and how they affect retention. It's going to become more clear as we go through, because I think there's better examples as we go. So, I mean, this stuff is pretty common sense. If we're doing a factorial design without replication, you're measuring something only once at one point in time. For example, a cross-sectional study. Pre-op relaxation techniques. So you're measuring their so you have a bunch of patients, you're measuring their anxiety post-op at one point after surgery. Just one point. That's without replication. If you had with replication, you would measure their anxiety after surgery, and then again, maybe 48 hours later, and again at a week, and again at 3 weeks, right? So you're going to do replication. So if you see these phrases without replication and with replication, we're just talking about basically the difference between cross-sectional and longitudinal studies. I don't see a huge difference. Like, I would line those up in my head to answer the question. The independent variable is nominal. They go together. They either go get the intervention or they didn't. Yes, no, yeah, okay. We talked about all this. So in a factorial design, your independent variable is going to be categorical and dependent variable is continuous. I actually have, before we move on, I have a giant chart that I made, and I'll send it to you guys, where it splits up all of these, like factorial, multiple regression, MANOVA, MANCOVA, whatever, all the ones we're going to talk about, and kind of like says what's the difference. So for in this case, categorical, continuous. In the next one, it's going to be continuous, right? It's a chart that just splits all that up. So it's like really quick reference. I don't know. I just find I can remember it better if I see it in chart form. So I'll send that to you guys. So don't worry if it's not all like sinking in right now. Okay, so multiple regression, it's basically the same thing. You have multiple independent variables, or factors. But this time, instead of them being categorical, they are continuous. So, oh, look, retention, see? I guess it wasn't a terrible example. So your dependent variable is retention, right? And then you want to study the 4 independent variables and how they affect retention. So job satisfaction, empowerment, again, burnout, workplace violence. Sorry, distracted. So we want to know which of these independent variables or combination of independent variables are the best predictors of retention. Which one of these independent variables affects the dependent variable or the retention the most, right? So when you have multiple independent variables that are all continuous, you can do this multiple regression, okay? Don't worry about understanding this. I feel like it's just way more confusing than it needs to be. All you need to understand is that the multiple regression is multiple independent continuous variables, continuous dependent variable, and it gives you the direction and strength, okay, of the relationship. So, for example, job satisfaction has a positive relationship with retention, and it's a very strong relationship. Empowerment has a positive relationship with retention, and it's very strong. But let's say workplace violence has a negative relationship with retention, probably also very strong, right? It's just giving you the direction and the strength, okay? And again, it's a very similar picture in your head to those scatter plots we did, right? Where you have a regression line and you can use that to kind of predict what's going to happen in the future. So if people are really, really satisfied with their jobs, less of them are going to quit, right? That's the point, I guess, of doing most of these studies, but also, sorry, here. Average variance above and below the mean. I don't know if I wrote that in there. If you don't know this by now, just go home. Just kidding. You guys know the standard deviation, what it is. So you've got your regression line as your best fit line. Again, just like your Pearson R, you've got that line. If it was a perfect correlation, it would be right on the line. So we want to see the difference between the line and the score. That's it. Okay, now, with your multiple regression, there isn't really any rule for how many independent variables you can have. You can have a lot, but the more variables you have, you need to have a bigger sample size. I'm guessing you'll get quite a few questions about error and sample size. If you're confused, just go with sample size. So because we're measuring more variables, there's more opportunity for error. Some textbooks say that you have to add 10 people for every variable or 15 people for every variable, whatever, but it doesn't really matter. You just need to understand that you need a larger sample size the more variables you have. So here's a good one. We're studying quality of life. That's the dependent variable. And we want to know how its relationship with age, gender, physical symptoms, and emotional distress. So you have 4 independent variables, all either ratio or interval levels of measure. When you see, I mean, this doesn't really matter, but if you see the word variance, it usually indicates that the variable is a continuous level of measure. So like a variation in quality of life, that hints to me that this is measured on an interval or ratio. Well, it'd have to be interval level. And then you know these are ratio and these are probably interval as well, okay? Now, she did say in class you can have a dichotomous variable in a multiple regression, but it's like gender, but that's pretty much the only time. In general, you need both independent and dependent to be continuous in order to do a multiple regression. And you understand that, right? Because how do you do a line of best fit with a dichotomous variable, right? So, oh yeah, sorry. I guess obviously that's not ratio, it's dichotomous nominal. Don't worry about how to calculate. Look, I even put you don't have to know. So let's just skip that. What is the point of confusing everyone? Okay, so just like with our Pearson R, it's the multiple regression is just giving us the strength and the direction, right? It's very, very similar to the Pearson R. It's just using multiple category or multiple continuous independent variables. So now there's there's a positive relationship between this and it's this strong, but remember before you don't really, it doesn't have significance, right? So let's see here. Oh, sorry, it's not about the significance. Do you remember before where we do the relationship at strength and direction with Pearson R, and then we do the Pearson R coefficient of determination, which is the R squared. It's the same thing that we're doing here. It's a coefficient. So let's see. It will show the percentage of variation in the independent or the dependent variable that can be explained by each of the independent variables. So very similar to that coefficient of determination, except now you're just doing it with multiple. So the difference between those is that you've got multiple regression, which is like your Pearson R, and then you have your, you have your multiple correlation coefficient, which is like your coefficient of determination in your Pearson R, okay? This one gives you the percentage of the dependent that can be explained by the independents. Okay, so again, it's R squared. And it just gives you, so if you can, this kind of helped me to picture it like this. So before, when you were doing a Pearson, you only had two variables. So it would say to you, well, trying to think what you guys did in your test. Oh, independent decision making and relational autonomy. And it turned out that something like 39% of relational autonomy was explained by independent decision-making scores. Awesome. But that means that 61% of the scores for relational autonomy were caused by something else. So that's where this comes into play. We want to know what those other things are that are affecting the dependent variable, in this case, relational autonomy, and how much of an effect are those things having. So we know that independent decision-making is having about 39%, right? If we did a multiple regression correlation coefficient, we would be able to tell, okay, what's making up the other 61%? Is it education? Is it RN, RPN, like professional designation, and so on, okay? And that's really, those are really very, very similar, the multiple regression and the Pearson R. The only difference is that you have multiple independent variables, okay? Whew. So let's talk about ANCOVA. So this is what we do when we know that there is an extraneous variable in our study and we want to name it, figure out how much it's affecting the groups and put it aside. So say you want to know what has the biggest effect on post-op knowledge, okay? So you've got a bunch of patients, they've just had surgery, you want to know, is it a video, one-on-one teaching, or group teaching that has the biggest effect? But you also know that stress can affect the ability to learn, right? So stress is going to have an effect on post-op knowledge, but you don't want to measure that. That's an extraneous variable. So you would use this ANCOVA to identify that and pull it out. And I'll show you, it makes more sense down here where there's a picture, I think. So your independent variables in this little story that I just told you are the different teaching methods, right? Your video, one-on-one, or group teaching. Your dependent variable is the knowledge, right? So you want to compare the means of 2 or more groups. Is the difference real, or is it just due to chance? Just like we did with the ANCOVA, right? But we also want to control for the effect of the extraneous variables. And the reason we call this analysis of covariance is because another word for extraneous variables is covariates. So other variates or other variables that are coming along with the ones we're measuring, but we don't really want them we don't really want their effect to come into the study, right? So you've got your independent variable, which is going to be categorical, right? Because it's like an ANCOVA. Your dependent variable, which is going to be continuous. And then your covariates, this is the thing you want to remove. And it can be continuous or dichotomous. So let's say we were talking earlier about, what was the example I was using? The post-op knowledge. And we want to take out the stress. So we would take the post-op knowledge here and the stress, which is the thing, the covariate, the extraneous variable that we want to get out of there. And we would figure out what that relationship is, how much of the knowledge or the dependent variable is explained by stress or the covariate. And then we move over here, we just take it out, right? So now we're left over with what is actually being affected by the independent variable. So I think what's really important to take home with the ANCOVA, again, is that we're talking about one independent variable with categories, similar to the ANCOVA. But what we're doing is we're taking the extraneous variable or the covariates, and we are measuring them and removing them from the study. Okay, or at least acknowledging that. I mean, you can't literally remove them from the study, but you can also do a multiple classification analysis after that. And it basically, all that does is it changes the means on the dependent variable after you remove the effect of the covariates. I don't think this is really important at all. Okay. MANOVA and MANCOVA. Almost done. This is a very, very similar to what we just talked about, the ANCOVA or ANCOVA, right? Except you have more than one dependent variable. And again, I get that this is going to be really hard to remember, right? It is, to a certain extent, it is just a case of memorizing, okay, MANOVA needs this and this. That's why I made the little chart, which I'll send you. But for now, we'll just go through it. You have one independent variable with categories, right? It's got to have more than 2 categories. Otherwise, it's a t-test issue or a different kind of test. It wouldn't be a t. You have one independent variable with a bunch of categories, and then you have more than one dependent variable. So you want to know, what is the effect of this dressing technique, which is your independent variable, on wound healing and on pain, which are your 2 dependent variables. Dressing technique has 3 levels. So it's ordinal. So you would think, okay, I'll do an ANCOVA, but then you realize, oh, but I have 2 dependent variables. And that's where you would do the MANOVA. Okay, and then the MANCOVA is same story as your as ANCOVA, and what was the first one called? Your multiple, wait, so confusing. Your analysis of covariance. Yeah, so same as your ANCOVA and your ANCOVA, right? You have your MANOVA and MANCOVA. The MANCOVA is going to take out the extraneous variables, just like we did up here for an ANCOVA. We do the same thing Here for the MANCOVA, the only difference is we have 2 dependent variables now instead of 1, okay? Okay, and then this last thing is pretty important. A factor analysis, not to be confused with factorial design, okay? When we started talking about multivariate statistics, the first thing I said was, we're talking about factorial design with all these different factors and blah, 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 right? So factorial design is different than, let's make sure we've got the right thing here, factor analysis, okay? A factor analysis is a study that you do that isn't necessarily about testing, it's not actually about testing a hypothesis. It tests the validity of an instrument. So some of you wrote about this in your paper. We talked about measuring for confidence to advocate for patients on a scale from, I think it was 0 to 25 or whatever, I'll say it was. Well, what instrument did they use? And is that instrument valid? Is it reliable? Because that's going to affect the study, right? So this is when we would do this factor analysis. We would test to see the validity of that instrument. So you've now developed an instrument to measure a construct, for example, confidence to advocate for patients. So you kind of know like what plays into that confidence, right? But you need to put numbers to the concept. You need to measure it. You need to operationalize. Remember in research, we talked about operational definitions and whatever the other one was, I can't even remember. This is what we're doing, right? So the factor analysis is what's going to determine how well the instrument is capturing all the different dimensions of that thing that you're measuring. So let's say you're using 20 questions on a survey to measure confidence to advocate, right? Some of those, you're gonna give that survey to like 500 nurses. You're gonna be able to pick through that and see, oh, okay, almost all all the people who are confident to advocate are clicking off, the same 2 or 3 questions they're saying yes or no to, but they're never ticking off like this other question, right? So you kind of play with it. You see how those questions cluster together, which ones are commonly selected, which ones are rarely selected, and you use that to test the construct validity of the instrument. So you take out all the items or the questions or whatever that are not measuring the construct and just keep the things that are closely measuring that construct. A factor analysis allows the researcher to determine how many factors or dimensions the instrument has. So which items in that instrument are most closely related to the concept that you're measuring. Which items means questions or like survey questions, right, are most closely related to the thing that you're measuring, okay? I think the really important take home from that is to remember, first of all, do not get mixed up with factor analysis and factorial design, and to know that the factor analysis is all about, testing an instrument, not hypothesis testing. Okay, and then I'm not going to go over week 12 because this is stuff, I mean, oh, I guess I could go through it really fast, but like this is stuff right? When you're looking at a study, at this point, what a study looks like. I don't remember there being like any questions. I don't remember though. It's a really long time ago. How do you look for error? You're looking for bias in the sample. You have, okay, this is a good example. So from what I remember, module 12 was just talking about the overview. When you have a study, how do you look at it and determine if there's error, or how do you analyze the study, right? So you're going to look at all the pertinent information. You're looking for error. One of the biggest biases that happens is you get a study that is, say, ICU nurses, but they only do the study on Monday to Friday between 9 and 5. So you're only getting a very specific population of ICU nurses, right? So who didn't participate is a really good question to ask when you're looking at the risk of error. You want to look at your attrition rate, how many people started the study and then didn't finish, and did those people who didn't finish have anything in common? Did they do the right test, right? So they've got categorical and continuous data, and they tried to do a pivot table or something, right? Did they do the like I was editing a paper where I think someone did a t-test, I don't remember, did a t-test instead of the Pearson R, right? Well, it's not actually giving you the information that you want. You can't draw statistical inferences from that, right? What was the level of significance? Is it too high, too low? This is stuff you guys should know. Simultaneously tech narrative, research question. Yep. Sometimes the research question, if you're trying to understand the meaning behind something, quantitative analysis probably isn't the thing you want to do, right? Yeah, this is stuff I'm not. Yep. This is all basically talking about everything from day one until now that you've learned. If there's a question on the exam that's saying, like, here's all the information, here's the research question, which test should the researcher perform? You're going to be able to answer that based on the first 11 modules. There's no point in going over this. It's just telling you need to know those things.